All right, this lesson will sort of be an all-in-one making scatter plots lesson and talk a lot about why we make scatter plots and with the things we have to consider. A lot of it you've seen in other places. I just wanted to tie it together in one lesson because a lot of these ideas are really neat for science. I want to make sure you've got a one note that's got them all in one place. So to be honest, the note is really most of the homework. There'll be a couple of homework questions, but really, really watch this video, fill in your note carefully, and try to capture all these ideas. And if there's a couple of new ideas in here that you haven't seen before, give those a good highlighting, okay? So here we go, making scatterplot. A scatterplot is a graph where each piece of data is represented by a dot. If that seems weird to you, just hang on and you'll see why we make them dots and what we can do with them when we do that. The most important things to remember are the rules about the scale. The scale must go by the same amount on each line horizontally, and the scale must go up by the same amount each line vertically. You get to choose. You can go up by any amount you want, but it has to be the same horizontally and the same vertically. Horizontal and vertical can be different. You can go by ones along the horizontal and go fives on the vertical. That's fine, but you just have to, whatever you decide for each axis, keep going up by that same amount. We want titles on the vertical and horizontal axis so people know what we're talking about, and the main graph should have a title as well. Also, the scale does not have to start at 0, but it's often a good idea. The only reason we wouldn't use 0 is that the numbers are unbelievably large. You can put those little breaks on your scale, a little lightning thing to extend your scale if you need to, but we generally suggest don't do that unless you really have to. So for now, a quick example to show what a scatterplot looks like. Here's some data taken from some newborn puppies, and the lengths and weights are given there. Now, we talked about independent and dependent variables in another chapter and got sort of down that path. And the facts are independent and dependent is way easier than what we've been applying and way harder at the same time. It's something you have to experience first. You actually got to do some experiments in science before independent and dependent will become clear. And what I mean by that is independent will be the variable you choose to measure at and say, okay, at time 4, we're going to take a measurement. Or at date 4, we're going to take a measurement. Or at temperature 5, we're going to take a measurement. The times you're taking measurements. So when you're actually doing experiments, it'll be obvious what you're using as independent and dependent. So I'm going to give a slightly different rule about independent and dependent just to get you through until that point when you're doing your own experiments in higher grades. And just say, listen, if in the first set of data, we're going to call independent, and the second set of data we're going to call dependent. Whatever's in the first column is probably going to be the independent variable, and the second one's going to be dependent. And I'm sort of lying here. To be honest, the length and the width of puppies, they're codependent. One's not independent and one's not dependent. But just for the sake of getting you ready for science, that's one little thing we'll use in grade 9 math to say, okay, well, we're going to take the first column as independent and the second column as dependent. With that, we're going to put dependent along or independent along the horizontal axis. That's normally the choice. So down here on my graph, I'm going to make the length go along the horizontal axis because that's the independent. Usually we put independent along the horizontal axis. So I'm just going to make a note about that too, that we usually go independent down here and we usually go dependent over here. I say usually, it's not really a rule actually. It's just something that we all do, so we're all doing it the same way. So if length was along there, then we're putting weight along here. And I think the weight was in grams. So I'm well on my way to having 3 titles here. I got the title there, and up here I'm just going to put a title, Puppy Data. You can do whatever title you want there. Okay, and so we got to look at what scale I'm going to use. Length here, I've got to get up to a height or a length of 17. I look like I got enough squares to go by ones. One little thing, well, I've got to go by ones all the way along, and I've got enough space here to write on every single line. But you don't have to. You could write on every 5th line and just write the 5s if that's more convenient. I mention that because I think that's what I might do in one of the later graphs, is go by a different scale. But you see, I decided to go ones on the horizontal scale, so I stick to ones all the way along the horizontal scale. For vertical scale, I got to get up to 53 I got to get to. And how many squares do I got? 2, 4, 6, 8, 10, 12, 14, 16, about 20 squares. So that means going up by 3s will get me there, but 3s is such an awkward scale. Me personally, once I get to 3s, I just go, you know what, I'll just go to 5s because that's easier. And I'm going to show you what I mean by not writing on every line going this way, even though I've got room to do it here, is that I'm not going to write on every line here. I'm going to write here. Oh, my screen's freezing here. Just a second. Let me just go out and go back in, and that should unfreeze that screen. Yep. Unfroze. Okay, so let me show you what I mean by going up by different, skipping lines here. So I want to go up by 5s, but I'm going to go 0, 10, 20, 30, 40, 50, 60, and that's more than enough to get where I want to go. You see, I did go up by 5s, but I only wrote on every second line just to make it a little more spaced out. It gets really cramped sometimes if you write in every single line. And then, okay, here's scatter plots in a nutshell. If you want to do scatter plots, what I'm going to do is put a dot to represent each puppy on the list. So the first puppy on the list is length 14 and weight 45. And that kind of graphing is the same kind of graphing that we've sort of been doing with Cartesian plane with X's and Y's. And we're just going to put dots along there for scatter plots. So 14 and 45. So length 14, that's about here, up to height 45. And on a scatter plot, I just put a dot there. Next one is 9 and 32. 9 and 32, and 17 and 46. 17, 46 would be right about there. 13 and 38. 13 and 38, right about there. 10 and 30. 1753, something like that. 1441, 14 and 41, and the last one, 10 and 35. 10 and 35. There we go. That's what a scatter plot looks like. A dot for each piece of data. Each dot you see here represents one of the puppies on the list. Got some questions to answer here. Which phrase describes the direction of the plotted points? The plotted points rise upward to the right. Yeah, that's the one. Right off the bat. That's the first answer. That's the one. They don't. The next one says fall downward to the right. No, they don't do that. The plotted points are scattered. Well, they are sort of scattered, but there is a trend here. So I see an upward trend, as you would expect, I think, from puppies. Upward trend. And the fancy word for this is positive correlation. So you may see that set of words in later math courses and certainly in science. What we're seeing is a positive correlation. As one variable gets bigger, so does the other one. You could also have negative correlation, and sometimes you could even have no correlation where you don't see it trending one way or the other. It says describe the relationship, and I'm going to keep it simple here. I'm going to say longer puppies. I'll say generally. Way more. Seems to be trending upwards here. Could I use the graph to predict additional measurements? And I'm going to put a giant yes here. And this is what this whole section is about with scatter plots, is making predictions. So I'm going to highlight predict. And by predict, we don't mean for sure we're going to know the answer. All I'm saying is that we can look at this graph and say, listen, if there was another puppy that wasn't on the list here and he had length 5, we could have a pretty good educated guess as to what weight he would be. You know, like, I don't know, like, let me just put a blue dot on here. If it's length 5, his weight's going to be, I don't know, somewhere in there. You see, I can sort of look at the trend and make a guess there, okay? And that's all we mean by can we use it to predict? And a prediction means we can make a good educated guess. So it wants me to explain here. Yes, we see a trend. Trend, what a good word in this section. When we see a trend, we sort of know where this is going. Okay, next thing on our list to talk about is a line of best fit. And a line of best fit on a scatter plot is a straight line that follows the trend of the points and has about the same number of points on each side. And I'm going to add another point here that I think is the most important. Can be used to make predictions. That's the important thing about a line of best fit. So let me highlight that. I wrote it myself and then highlighted it. That's how important I think that sentence is. So, for each scatter plot, draw the line of best fit. Okay, my goal is to have about the same number of points above and below and follow the trend. I see in this first graph, it's sort of an upward trend. And I need about the same number. Oops, the screen just jumped on me there. And I got to tell you that this drawing a straight line in here will not be simple. So I've got a ruler sitting on my screen here, and we'll see how this goes. I hope it comes off pretty good here. Something like about there. Not too bad. You can see it's a little wobbly. Did I get about the same number of points on the top and bottom? 5 above, 3, 6, 7 below, but I'm sort of touching one there. So it's about 6 and 6. Again, we're not trying to be perfect here. If you want perfection, actually, we don't get too crazy about perfection with drawing it by hand because we have computers. As you move up in grades, you'll find a way to get a computer to draw this trend line for you, and so you'll get a perfect trend line. So we don't get too wound up. If it looks pretty close, we like it. And then this one, somewhere right about there. How did I do that? About 4 below, about 5 above, and I hit 3 of them. Yeah, pretty good. Okay. Notice this would be positive correlation because it's going upwards, and this would be negative correlation because it's going downwards. And we definitely see a trend in both of these. If we didn't see a trend, we wouldn't have positive or negative correlation. Now, why would we want to draw a line of best fit in a scatter plot? In big letters, to make predictions. That's what it's all about. And I'm going to do an activity in just a few minutes that really shows off what I mean by making predictions. So here, a few more to draw the line of best fit on. Let me get my ruler out here. Oops, my screen jumped on me again there. Somewhere about there. Hopefully you have better luck with your ruler on your page than I have on the screen here. This one, not as easy. They're sort of scattered. You might not believe there's a line of best fit. It asked me to draw a line of best fit, but if that data actually come up, you'd be like, I don't even know if it makes sense to draw a line of best fit here, because it doesn't always make sense to draw a line of best fit. Something like that. 3 above, 3 below, and touching 3. Pretty good. And ooh, okay, definitely this one here, I would say, is no correlation. I'll draw the line of best fit because they asked me to, but wow, I think those are too scattered. We might call that no correlation. Okay, here's the main activity that I want to talk about and why we do things like this. Forensic analysis. Anthropologists and forensic scientists use data to help them determine information about people. Often only a few bones are available or the evidence is inconclusive. In spite of these difficulties, by accessing the information in large databases and investigating relationships between data, scientists can determine information about the height, age, and gender of a person they're examining. You can make unbelievable predictions, usually very accurate. Of course, there's times when special cases come up, but you can use the length of these bones to figure out how tall people are, how old they are, these type of things. So here's some data from some humans. Construct a plot for the following from the following data. They gave some radius and humerus numbers here. Now here's on the picture here. Here's the radius length. There's the radius bone, and there's the humerus bone. So on a bunch of skeletons, they measured or on a bunch of people, they measured radius and humerus to see if there was a trend there. And as you'll find, I'm sure there is. So here I'm going to put on those data points: 25 radius, 29.7 humerus, right about there. 22, 26.5, right about there. 23.5. 27.1, right about there. 22.5, 26. 23, 28. 22.6, 25.2. 21.4 and 24. 21.9 with 23.8. 23.5. 26.7. Maybe a little higher than that. There we go. 24.3 and 29. And 24 and 27. I'm going to zoom in on that so you can really see the trend. You see it trending upwards there? There we go. Now, it says circle the point on the graph that has a really small highlighter here. 21.9 is the radius, so that was the 21.9, 23.8, number 21.9, 23.8, right about there. There's the one they're talking about. What was the corresponding humerus length? 23.8 centimeters. Draw a box around that represents the humerus. That's 27.1. So now we got to go the other way. Humerus 27.1. When the humerus was 27.1, we had this one point here. I can't draw a box, but I highlighted it there. And that's the 23.5 one. And as the length of the radius gets longer, what happens to the length of the humerus? It gets longer as well. So what we'd have is positive correlation here because it's going upwards. Now, do you think that we can use the length of the radius to estimate the length of the humerus? Yes, because there is a trend. And it's a little scattered. Will the prediction be great? Maybe not, but we can make a prediction. Do you think that you can use the length of the humerus to estimate the length of the radius? Yes. Because there's a trend. There might be a better way to phrase that, but I like that trend word so much I'm trying to use it. Use a ruler to draw a line of best fit. Okay, here it comes. I'm going to try and do it in a lighter color. You'll find sometimes line of best fits are good in a light color so you can really see what's happening. So I've gone with orange here. Something like that. I went through 3 points. I got 3 above and 4 above and 3 below. Not bad. I'll take it with the difficulties of drawing on a screen like this. Got a check. I like putting check marks when I have a list of things to do here because then it reminds me I did it. Okay, this is the big question, the most important question of this section. Use your line of best fit to predict the humerus length for radius length 22.7. So what I'm going to do is go back to my graph and go up to about 22.7, which is right about here, and go up to the line and go, okay, it meets the line right there. Humerus 26 is my prediction. Now we call this interpolation, and the reason it's called interpolation is because it was inside the data. You see, I went inside the number of dots. I was in this section here. And when I'm looking within the dots I've already got, we call that interpolation. Next, make the following predictions. Radius 25.2. So radius 25.2. 25.2 would be right about here. Up to the dots. Right about there, halfway between 28 and 30. Looks to me about 29. You will do better with your calculator than I was able to do, or with your ruler. And then radius 28. Ooh, that's way out here. Interesting. That's outside the dots. I had to use the line of best fit this time to get humerus length 32. So explain the difference between interpolation and extrapolation. Interpolation is inside the data given. And extrapolation is outside the data given. That's where you really have to use that line of best fit, is when you go outside those points, okay? Okay, so I hope that gives you an idea of how to do scatter plots and line of best fit and using them to make predictions. That's the big thing, is use that line of best fit to make a prediction. Very little homework here. I would keep this sheet for your science classes, file it away, make it, stuff it into the front of your binder, because a lot of these words will come up again in your science classes later on. Okay, that's it. Do your quick homework and have a great day.